And it says for n equals 2. Tomorrow will be n equals 3.
All right, so before I get started, I forgot to do this yesterday. I was supposed to have made some advertisement here for a new journal in mathematics. This journal of UMALCA. UMALCA is a Latin American mathematics association, and this is a general journal, field journal with some pretty nice it's called Mathematica, and has some pretty nice editorial board members. And there. So we are open for submissions, and it's supposed to be a high-level journal. Welcome submissions. Now, find controls here. Okay. Let's get started with lecture 2. Okay. So, first of all, previously, what happened? So first of all, I just want to make some short notes here, short remarks. First of all, with respect to rigidity, which is criteria or thresholds where you get energy conservation. I just want to note that all of the 3D results that I mentioned, they are actually criteria. So we have no existence results known in 3 dimensions for solutions who live in L infinity in time BH5/6 and L3 in time B1/3 3C0, which are the thresholds where you get energy conservation. And I contrast this with what we showed in 2D, where you do have existence results. So we're actually talking about objects that exist. Okay, weak solutions of 2D order with velocity in L infinity W1. All right. Another comment that I want to make is that the results that I mentioned on conservation of energy, efficient vorticity is LP. I showed you what happens with physically realizable solutions, but there are other approximations that lead to such weak solutions. For instance, numerical approximations given by the Vortex-Blob method, and those were also shown to have energy conservation if P is greater than 1, and even local energy balance if P is greater or equal to 6/5. We, meaning Alexei, Roman, Milton, and I did not discuss local energy balance for the physically realizable. We have no idea whether it holds or not. I imagine that it should hold the same kinds of P's, but we did not look at this problem. Okay. So this is work due to Siampa Kripa Spiritu from 2 years ago. Okay, I also mentioned extension to axisymmetric boiler, and I said that the result is slightly unsatisfactory. So this is a result due to Nobili and Seitz, published this year, actually 2022. Its initial vorticity is non-negative, and the first moment is finite. Okay? And this quantity, omega not over R, so we'll talk about its symmetric flow, so R is the radial variable. If that's an LP, the half plane, so with respect to this weighted measure here, R dr. Okay. Where's my, there it is. Just having a hard time finding it. Okay. All right, R dr dc, T greater than 3/2, then you can show energy conservation as well. The reason that this is slightly unsatisfactory is that this P greater than 3/2 here is not the right exponent for strong convergence. The exponent should be 6/5, should be much smaller. Okay, but so that's what we have. All right, so L infinity W1 P greater than 1, 2D physically realizable solutions conserve energy, and this rules out that they could be convex dissipation while solutions are solutions with anomalous dissipation. Where anomalous dissipation is used in this broad, vague way where simply energy is not conserved. Okay, so this supports that you can look at the vanishing viscosity selection criteria. Of course, as a selection criteria, this statement is weakened by the fact that other solutions also conserve energy within this class, within this LP P greater than 1 class, such as the vortex blob solutions attainable as a vortex blob approximate limit, or solutions attainable as weak limits of exact solutions with smooth initial data. Still, we are looking for selection criteria, and as Idris mentioned on Monday, this idea of having a selection criteria coming from vanishing viscosity is also present earlier in the work by Claude Idris and Emil Wiedemann, 2012, where they look at shear flows in 3 dimensions. And they notice that the vanishing viscosity selects one weak solution. We have a multitude of weak solutions, but only one of them is attainable as a limit of vanishing viscosity. Symmetry breaking, which Idris also mentioned, is another instance of selection criteria. It's also avoided by physically realizable solutions. Okay. Now,
just to be in our case, we don't call it selection criteria. We call it ruling out, because we don't, I mean, I personally, I don't know about my collaborators. I am not really some sense fan or like a fanatic about uniqueness. So therefore, I'm talking about like ruling out, like namely which solutions cannot be physical. I might have many physical solutions, which are many uniqueness. So that's why
we are being a bit more ambitious.
Yeah, that's what that's so that's why we call it rule it out, not selection.
Yes, I remember. Okay, now let's say Rahman, Milton, and I were feeling pretty good about ourselves about this conservation of kinetic energy for supercritical solutions. And we began feeling very good about ourselves until these guys here, Samuel Alcala, Sid Mishra, and Carlos Perez-Pulido, showed that actually our result was quote trivial or obvious. So I'm going to tell you about what their result was. So they proved that having a conservative, physically realizable solution is equivalent to strong convergence of the realization. This result really took me by surprise. I thought that you needed both strong convergence and something about the dissipation rate, and it turns out you don't. They're actually equivalent. Strong convergence and having a dissipation rate which vanishes are equivalent. All right, so I'm going to tell you about their result because I think it's a really, really neat result. Okay? So the key object here are L2-based structure functions. So let's let you be a physically realizable weak solution. In other words, a weak solution 2D, this is really 2D, Euler, which is a weak limit of vanishing viscosity solutions. Okay, and consider a physical realization, you super that. Okay, and now I'm going to introduce what Alcala and Mishra has been called their structure function. So they have 2 different kinds of structure functions. One called S2, okay, which doesn't have time in it. Okay, so time is just a parameter. So this is all on the torus. So we integrate on the torus, on average in a small ball BR, the translation, the difference in translation, increments, the velocity squared. Okay, you raise that to the power of 1/2. Okay, and then S2T is when you look at the average in time as well. You integrate in time as well. All right.
It's just integrated in time. It's not average.
Sorry?
It's not time average, or it's.
It doesn't matter.
No. This average here is only in space.
Okay.
This is only in space. Okay. Okay. So say phi is a modulus of continuity. If phi is greater equal to 0, and it vanishes our viscosity. It's what you want. Okay. And here is their theorem. Samuel Alcala, Sid Mishra, and Carlos Perez-Pulido. Suppose U naught is a physically realizable weak solution with initial data U naught. U naught is L2, and consider a physical realization. Okay. Then the following are equivalent. U nu converges to U strongly. LP in time, L2 in space. For some P, any P greater or equal to 1, less than infinity. 2. There is a modulus of continuity such that the structure functions are bounded by this modulus of continuity uniformly with respect to D. And 3, use a conservative weak solution. It's a very nice theorem. It's quote obvious, unquote, but as my good friend Idris Titi told me today, what makes mathematicians tick is to prove or justify obvious results according to engineers.
And its equivalence from 3 to 1 as well.
Yes, they're all equivalent.
And how that
Okay, so
can prove.
I'm actually going to discuss the proof because I was surprised. Okay. By the way, Samuel Anthaler just finished his PhD last year. So he took a long time to. He just finished. Pretty impressive. Okay, so first of all, the first step is pretty simple. If U is conservative, then U converges strongly. Okay. So how do we see this? So for any T, we have assume that you have a conservative weak solution, so the energy is conserved. So T times capital T times the L2 norm squared of U times little t is the same thing as the interval from 0 to t of the energy. These are all constant. Okay. And the energy is weakly lower semi-continuous, so this is less than or equal to the length of the energies for the viscous velocities, which of course is less than or equal to the lim sup, which is less than or equal because the viscous energies are decreasing. This is less than or equal to capital T times the largest one, which is the initial energy, which is equal to T times the energy for the initial data. Because of in the definition of physically realizable solutions, we assume that the initial data is convert strong. Therefore, since we have a conservative weak solution, this is equal to this, okay, and all the less than or equal signs are actually equal signs, and you have convergence of norms. L2 norms converge. Now, physical realizations are weak limits. When you have convergence of norms plus weak limits, weak convergence, that implies strong convergence. QED. Okay. The rest of the story, the rest of the equivalence, would be this to show that nu converges strongly for some LP in time, L2 in space is equivalent to a bound on the structure function, and that implies energy conservation. Now that's a little bit abstract and complicated, so instead I'm going to outline the proof, slightly simpler statement, where instead of having a general modulus of continuity phi, I'm going to look at a modulus of continuity, which is actually power of R. So I assume that S2 without time is like less than or equal to constant times R to the alpha for some alpha between 0 and 1. And I'm going to show that that implies energy conservation. So to show this step over here. Okay. Afterwards, I will discuss briefly the general case of R and S2 of T. What changes? Okay. So let's assume that S2 behaves like R to the alpha. So the increments are like R to some power alpha. Okay. Uniformly with respect to nu and time. And let's show that this implies compactness in L2. Okay. That's the first step. So this is actually a rereading of something called Kolmogorov compactness criterion, plus the fact that you have control on time, on the temporal behavior of your units. Okay, and so that plus an Abelian type result where you have control how to step up in time, and you have compactness in space, that gives you the compactness in C0T L2. Okay, so Kolmogorov matter. This isn't working. All right. Anyways, so because of this, the Kolmogorov compactness criterion basically tells you that if the transitions are continuous, or vanishing, uniform and continuous, then you have compactness in L2. So this gives you the compactness in L2, and then the time compactness comes from the temporal estimates for U, dt, U nu, and then an abelian type result. Okay, so so we have shown this that S2 behaving like R to the alpha implies energy conservation. Right? And now what we want to show is the dissipation rate vanishes. I want to show that, we've shown that it implies compactness, L2 compactness. Okay? Now I want to show energy conservation. How does that come? So it all starts out with a lemma that I can interpolate the L2 norm of any function in terms of the gradient of omega and this structure function S2. I mean, my S2 is behaving, is playing the role of my vorticity in LP from the last lecture. Okay. So if I use that hypothesis that S2 actually goes like R to the alpha, then what I get is the L2 norm of omega is bounded by the gradient plus R to the alpha minus 1. R to the, yes, alpha minus 1. Okay, and alpha is less than 1. Okay. So I can choose R to optimize both terms, and I get that omega L2 is bounded by the gradient of omega to the power 1 minus alpha over 2 minus alpha. So this is starting to look a lot like the estimate that I had from last lecture. Okay. So we use the end-stream dissipation inequality. T of omega L2 squared is bounded by mu times the L2 norm squared of the gradient of omega nu. Substitute the estimate that we get from the structure function, and we have this 2 times 2 minus alpha over 1 minus alpha. This rereads as this differential inequality. dy dt is minus c nu y to the 2 minus alpha over 1 minus alpha. And as before, the exponent is greater than 2. And that's the important thing here. 2 minus alpha over 1 minus alpha is greater than 2. Okay. So the corresponding ODE, assuming omega is an LP, p less than 2, before was dy dt is minus c nu y to the 2 over 2 minus p. With this exponent greater than 2. This was from last lecture. Okay. All right, so if we integrate the ODE, we get y of t is bounded by this object here, and we have this minus 1 over minus 1 minus alpha. So this is a negative exponent. So therefore, or in other words, this, okay, therefore, we can estimate the energy dissipation term directly as this. It's a constant that depends on alpha, and then you have omega naught nu L2 to the minus 2 over 1 minus alpha to the power alpha, nu to the power alpha, and this guy here again to this negative power. The point is that the initial data measured at L2 is raised to a negative power. Okay? And this nu is raised to the power alpha, which is less than 1. But when you multiply this, when you integrate this, you're going to get this goes to 0. Okay? So I'm sorry. Nu to the power alpha is positive, so this goes to 0. Okay. As before, I don't know if I started out with a viscous initial vorticity, which is infinite in L2, but even if it isn't, it goes to 0 eventually. It goes to infinity, so. Okay. All right, so the energy dissipation is to 0. I've already shown that it's compact in L2. And as before, that's all I need to show energy conservation. The rest is follow the other argument. Okay. Okay. All right. So how does the general case work? So it's a very simple idea. Okay, and so far it looks really a lot like the previous result. Okay. Now, for the general case with the modulus of continuity, you want to show this, that U nu converges strongly for some LP L2, if and only if this time average modulus of continuity behaves like phi over R for some phi, and then that implies energy conservation. Okay, now you start out with an initial velocity, which is L2. So you already have a bound in L infinity L2 for the velocities. Okay? And this implies by interpolation that U nu converges strongly for some LP here, if and only if it converges like L2, L2. So you can reduce the case L2, L2. All right. Now, how do you go from the modulus of continuity to strong convergence? This is pretty simple. It's just an extension over of compactness criteria. Pretty simple. So the energy conservation will use compactness of U nu in L2, L2, and an estimate on the dissipation term, which is similar but more complicated than what I had before. I'm not going to have these explicit bounds for these alpha, et cetera, but something very, very similar to what I did before still works. Okay. Okay. Now, how do you get the modulus of continuity from knowing the strong convergence? Why is that equivalent? And what you do is you look at the compact closure in L2 of the viscosity of the viscous approximations you knew. Cover these with some balls, radius epsilon. Okay. And use the fact that it's compact to extract a finite subcup. Okay. All right, so I'm going to set phi of R to be the supremum of S2T of U R for U in this compact set K. Then I can measure this S2T by the triangle inequality. It's going to be U minus UL plus UL, where ULs are these guys here, these finite number of centers of these balls in L2.
Yeah,
So since U is going to be in K, then it's going to be close to one of these ULs. Yes.
Maybe something missing. What do you mean by the compact closure of solutions? So you use solutions and interval 0T?
Yes. This is an L2, L2. Compact closure in L2, L2. L2 in time, L2 in space.
So closest sequence in L2.
It's a bounded set. Okay.
So why the closure is compact?
No, the closure, and take the compact closure, and put all of the possible limits.
Closure is closure.
Have to be compact.
Why it has to be compact?
It could be the whole ball.
Sorry?
Could be the whole
Wait,
ball.
okay, so first of all, I'm assuming here that you knew converges strongly.
Oh.
I'm already assuming, in a sense, I mean, there is only one additional guy that I'm putting.
No, that makes it.
So the assumption is that you knew converges strongly. So that setting it up this way makes things easier because I have topology that can cover things by balls and extract finite subcups. It's just that.
Even if the converge strongly is compact, once you
Yeah.
put it at the end of it.
Yeah, I'm just putting the limit. Okay. All right, so then I have this is bounded by 2 times this plus ST R, and it's easy to see S2 of ULR goes to 0 as R goes to 0. All I need to show is that this object that I showed that I have here vanishes as R goes to 0. It's clearly greater than 0. To show that this is a modulus of continuity, all I need is to show that this guy is greater to zero and vanishes as r goes to zero. So it's easy to see that for individual functions, it vanishes as r goes to zero. This is one of these Lebesgue continuity criteria.
The ULs need not be solutions at all, they're just points in them.
These guys are just in this K. Just for any translations are confused.
Yeah.
No. Just that. Okay. All right, and the rest is just a matter of 3R. Show that this goes to zero. What you need to show is that for every epsilon, you find a delta, such as R less than delta, then this thing is less than epsilon. That's an epsilon over 3. Okay. So, what are some consequences of this? First of all, if I take an initial velocity, which is L2, an initial vorticity, which is in space, in space X, which is compactly embedded in H minus 1. And what this means is that the corresponding velocities are going to be compact in L2. And then if I can prove that this estimate in X is preserved by the viscous flow by Navier-Stokes. And if X is a rearrangement, well, it doesn't have to be rearrangement, then any weak limit of mu is energy conserved. So this extends the result when omega naught is in LP to any such space X. So again, take an initial vorticity, which is in space X, such that I know that X is compactly embedded in H minus 1. And the Navier-Stokes evolution preserves the space X. Then any weak limit of mu is energy conserved. Examples of such bonic spaces X, LP is compactly embedded in H minus 1 because W1P is compactly embedded in L2. Here's another space that's compactly embedded in H minus 1, L log L to the alpha. So these are Orlik spaces or Sigmund spaces, depending on what your community is. And basically they correspond to function spaces such that something that looks like entropy, integral of omega naught times the log of omega naught power alpha. That is integral. All right, these are weird spaces. They're called Lorentz spaces, and they're different from the Lorentz space that Maniacola and Gabriel used in non-uniqueness, because these guys are subsets of L1. Okay. And it turns out that if you look at the case Q equals 2, which is not contained here, Q is strictly less than 2. Okay. And for the case L12, that will be the largest rearrangement invariant space, which is compactly embedded in H minus 1. It's a nice space to work in. It's basically the largest, if you want, it's the largest space for which the velocity, the corresponding velocity is going to be an L2. But L12 is not compactly embedded in H minus 1. It doesn't give rise to compact velocities in L2. L1Q does for Q less than 2. So all of these are rearrangement invariant subspaces of L1, which are compactly embedded in H minus 1, and such that the Navier-Stokes evolution preserves the initial estimate. In other words, the X norm of omega mu is bounded by the X norm of omega naught. What about L1? L1 is a weird space because if the vorticity is in L1, 2 dimensions, you don't know a priori that the velocity is in L2. That's an extra assumption, an extra hypothesis that you have to make. So actually L1 intersects H minus 1. What happens in L1? What happens in bounded measures that intersect H minus 1? These are cases of physical interest because they correspond to both sheets. Now, Delors and Kiwu in 1993, they proved that there were no concentrations of vorticity. Massive vorticity in small balls goes to 0. They don't concentrate, they don't become direct. So it's still open whether you can have concentrations in velocity. In other words, do the velocity approximations converge strongly in L2? Do the lower weak solutions to the vortex sheet initial data problem conserve kinetic energy? We don't know the answer to these questions. Delora constructed his weak solutions by the approximation method. We do not know whether the corresponding velocities converge strongly in L2. All we know is that this doesn't come from any upper estimates or from any sublime embedded fields. Okay, let me switch gears and let me talk about, I'll come back to this eventually, but let me talk about force, fluid flow, and energy balance. This is sort of an expansion of the talk that Milton gave here about a month ago. So Euler-Navier-Stokes with forcing, the system, and energy balance. Energy is no longer conserved, but it's balanced by whatever is input by the force, the external force F. And what we want to know is, can we find regularity conditions on the force state which lead to energy balance solutions? Why? Low regularity flows are a natural context for turbulence, and forcing is one of the preferred mechanisms to generate small scales. So we want to know what difference it makes in a small scale. We need to amend the definition of physically realizable solutions to include the behavior of the forcing. So the viscous forces have to converge weakly to the Euler force, the inviscid force F, weakly L1 and time L2. And then we have the following theorem, just to work with Milton. Okay, so if you have a physically realizable solution with an external force F, and such that the physical realization satisfies another estimate. So the initial vorticity is an LP, P larger than 1. The initial vorticities converge strongly, no longer enough to say that they're just bounded. They have to actually converge strongly to the initial vorticity, LP, and the curl of these forces has to be bounded. L1, LP, L infinity, L2. These are very strong assumptions, not satisfactory at all. Then it was energy balanced. Still, I'm going to go through the proof just because the proof teaches us how much more complicated things can get when you add force. And I'm going to come back to this in the last lecture tomorrow. All right, so as usual, we start from the vorticity equation and assume that the initial vorticity is not an L2, otherwise everything is trivial. Take the curl of the FU and we get these G news, and we incorporate the forcing term and multiply by the appropriate thing, which in this case is omega nu. We get this energy estimate here, which can be rewritten. It's just some constant nu, omega nu L2 squared to this power 2 over 2 minus P, plus this extra term here, this growth term, which comes from added force. So I have this minus a nu here, which is a nice term, which is what I had before, and plus this, which comes from force.
Sorry, is there an LP?
Sorry.
There's maybe I missed something, but there's a P on the right-hand side, but no P.
Here.
This is coming from the gradient of the omega, the Poincaré like.
Yeah.
Oh, okay.
Yeah. This
This is from the Laplacian.
Okay, I just.
Yeah, this came from, I already used it.
The initial Poincaré like.
Thanks.
Okay,
Where is
so
the G? Where is the G? Which is space? G.
G is L1 in time LP bounded, L infinity L2. Very regular, very regular. This is not a good result.
Sorry?
This is not a good result.
I'm not saying about good, I'm just trying to follow
Okay.
the argument.
Just sort of a first one. Okay, so then what we need to prove is, since we already started with an omega naught, which is now P, omega naught U, which is bounded now P strongly, then we get just by integrating once that the velocities are going to be bounded in W1P, out fitted in W1P, and therefore compact in O2. That's not a problem. So all we need to do still is to look at the dissipation, which is U dissipation term, U times integral in time of the entropy squared. I need that to vanish. Okay. So instead of getting an estimate, the rate, et cetera, like we did in the previous case with more forcing, I'm going to have to use asymptotics. So we write C to be the entropy. The energy estimate that I get is written in terms of C in this form. And this 2 over 2 minus P is greater than 2. So I have something that I have very strong decay, and then I have this slow growth counteracting. All right. Now, Z naught of Z nu of 0 goes to infinity, fine. But for any positive time, it's fine. No matter what it is at time t equals 0, if you turn on time, this parabolic regularity gives you that it's fine. So alpha is our exponent, 2 over 2 minus P, which is bigger than 2. And we divide the proof in several steps. Step 1, we look at the inequality. You're starting from some time delta positive at which you have something finite. Then you show the ground wall that C is bounded between 0 and N. Okay, so we look at the nonlinear term, that the flux term is minus A nu R d alpha plus B squared of nu. This guy is concave. This. So you look at the difference, C nu minus M nu prime, and that's bounded by phi nu sub M using cavity and C nu minus M. And then you just use ground from this. So what is left is a study of the ODEs for M. Now, phi nu, my flux goes like this. There's a certain point where it's 0 and then it becomes net. Okay. So the key is the equilibrium. Okay, so since I have an ODE, if M starts above this equilibrium, it will tend to the equilibrium. If it starts below, it will to the equilibrium, but it can't cross it. Phi changes signs from plus to minus. So if you're below the equilibrium, then you're below it for all time. And thus C nu is below the equilibrium. And this equilibrium, the way it scales with nu, is enough to show that nu times that integral vanishes. This nu goes to 0. If you're above the equilibrium, then phi is going to be negative. So you decrease towards the equilibrium. Okay. But then you need to consider 3 different cases. With the lim sup of Z nu of 0, which I don't know if that's infinite or not, over R nu, when it's less than 1, equal to 1, or greater than 1. When it's less than 1 or equal, that leads to Z nu of t less than or equal to some constant times the equilibrium. And again, you have the proposition. Dissipation term vanishes when nu goes to 0. Okay. It's the third case, which I remind you is when this is greater than 1, this is big, which is the typical case that you're going to be worried about because you want Z nu of 0 to be going to infinity. Okay. And since this exponent here is positive, and nu is in the denominator, so does this guy go to infinity. So this is there's a competition. Okay. So for that, you actually need to basically solve the M equation. So you write phi nu to be this integral here. Okay, but you can, since lowercase phi nu has a 0 at r nu star, you can only integrate this from r nu star upwards. Okay. So first, so you need to show some properties of this phi nu. It's strictly decreasing with an inverse. It has an inverse. The limit as r goes to infinity is 0, and the limit as r goes to equilibrium from the right is plus infinity. And this is just calculus. It's pretty easy. Okay. And from here, you show that phi nu therefore is a diffeomorphism, and the solution m nu is given by this. It's explicit. Well, both explicit. You started from t equals delta, and you move on. Okay. So now you take the limit as delta goes to 0. It's not trivial, but it's okay. And you can show that, and since c nu of t is less than m nu of t for all time, you can show that c nu of t is less than or equal to this phi nu inverse of t. In other words, you can get rid of this delta. Okay. And of course, if c nu of 0 happened to be infinite, okay, then phi nu is 0. So you can get rid of this. Okay. So you interpret this accordingly. Okay. All right, so now we need to introduce this R nu double star. So R nu double star is the guy for such that if you're above him, then the term that dominates in the OD is the faster growing term with this 1/2 minus alpha. So 2 minus p. So phi nu of r for bigger than this R star is bounded by this very strong term. And it's going to be negative. Okay, so step 3, you estimate your dissipation term, nu times integral from 0 to t of z nu, by the integral from this r nu plus stuff that you only see r nu double star here with a nu. And here you have nu times r nu double star and phi nu of z of 0, which you know is going to 0. It's either equal to 0 or it converges to 0. The proof of this inequality is just, again, calculus. You have to do a smart change of variables and some integration vectors. And this is enough to conclude the proposition because nu times r nu double star, in the same way as nu times r nu star, which we used before, that vanishes. This term here vanishes for the same reason, even stronger. Okay, and this term here will vanish because if you're if you're in this region where you're above r nu double star, then this strong growth rate, whatever, something r to the power alpha takes over. So this becomes, so you can estimate phi nu here as 1/r to the alpha minus 1. When you integrate this, you get r to the alpha, and then nu times that will vanish. Or 2 minus alpha, sorry. And nu times that will vanish. So that's when you need alpha is less than 2. It's greater than 2. So. Okay. All right. So the key points of the story were the fact that phi nu was concave, so that you could do an adapted ground wall. And we needed not just estimates, but we needed precise asymptotics. Everything here had this, you have an ODE with coefficients which depend on the parameter. Try to figure out delicate estimates with respect to. Okay, so finally, I'm too early today. Some comments and conclusions here. What we've learned is that the Onsager scaling is not the last word on inviscid dissipation. In 2D, you do have a dynamical mechanism which avoids anomalous dissipation, namely the vanishing viscosity being a solution of Navier-Stokes. We have no idea what happens in L1. Okay, so we have no tools, And what we'll see in the last lecture tomorrow is that there is a big discrepancy with respect to what we know about vorticity in L1, the vorticity equation. Okay. I already mentioned this, that bounded energy is an extra assumption if the vorticity is only L1. Well, no, but it is that it's only L1. And these cases, vorticity in L1 or a bounded measure, are actually arise in cases of physical interest, such as sheets. And finally, there is no version of singular color result in the case of forcing. What are really the correct assumptions of forcing so that you get an infinity of criteria, equivalence criteria? And this is a subject of work in progress, actually. So I'm finishing early. Okay.
Questions from the audience? Yes.
What about annular dissipation of entropy?
Right, that's the subject of tomorrow's lecture.
Okay. And I had another question.
After.
So usually, I mean, so coming from physics, we know that energy is conserved in inverse cascade. And so we put some mechanism of dissipation at large scales, like something like inverse power of Laplacian. So usually we have as a tool. So my question is, could it be something to consider from the point of view of dissipation? In the sense that you put so instead of putting viscosity, so consider some inverse power of Laplacian.
Where?
And see if when your viscosity is going to zero, you get a finite amount of kinetic energy.
The hypoviscosity.
When your hypoviscosity is going to zero,
No, I have no
keeping
idea.
forcing constant.
I have no idea. That's interesting. Right.
That's it.
No. The answer is no.
The answer is no.
That's okay. Because hypoviscosity takes care of the large scales, large Fourier numbers, not the small fine scales.
Okay.
All these structure functions about R small, etc. But what's happening for small scales for high wave numbers where the viscosity is active, and that's your interplay between viscosity and R. All these things. So in this case, it's active.
Except if you tune the box size. So if you,
well,
at the same time you make the box size.
So you are playing now with another parameter, which is the size, which is scary. Little R versus big L. That's the other questions in the audience? In the virtual audience, no virtual audience. I have a question, please. Can you? You have a question? Sorry.
Can you show the assumptions on G? That you said you said it was kind of very strong assumptions on the G, the curl of F. Could you show that?
Very strong assumptions. I agree with you.
Well, I was just quoting what you said, but did you have a feeling that if this is it's coming from the structure of that ODE that you use?
Yeah, it comes from here. But this is sort of the cheapo estimate. There's other ways of estimating. It's just this is the cheapo estimate.
But it's like it's like kind of a Sobolev embedding issue, or is that you get just the wrong structure in this ODE that's worth both?
Well, okay. So when you multiply this, you multiply this by omega. Okay. Let's see. First, this assumption here, this guy being finite, comes from the maximum function to the maximum of the LP norms of vorticity, the 2D. Okay, where this comes from, and this assumption here just comes from G times omega. There's other ways of estimating.
Can you show us the structure function? The structure function.
Sure. Something like the structure function has appeared recently in the literature in this work by Vlad and Peter, also Theodrivus. But I mean, I think, I didn't bother saying this because I think this is just so ubiquitous in turbulence that.
It's okay, I've seen your actual
Almost.
records. Here. So, I mean,
Okay, so this is the S2, not the S2T.
that's what I said, it's structure function. So, yeah.
There's two.
No, I just basically want to make a general comment.
Okay,
General comment is basically when you put R to the alpha, it's quote to quote, you're assuming that you uniformly belong to some kind of alpha base of space.
absolutely. This is like any H alpha. In fact, this
It's
is
like
actually-
it's almost like Hölder uniformly
Yes.
continue.
Yes,
That's my comment. So in some sense.
but alpha is anything, any
I
possible.
understand. I'm just basically trying to connect
Yes,
with what we know.
Okay.
We are assuming that uniformly in the viscosity, the solutions of Navier-Stokes are sort of belong to some regular space with Hölder continuity of
the
certain.
2D they do.
I understand that.
All right,
I'm just basically trying to relate to what we know in the what's happening. I mean, it's just, I mean, for me, it's like, it's not, oh, here's an estimate and here's,
sure.
this is inspired by basically the issue about,
Absolutely.
it is almost like Hölder with some fancy averages, etc. And this has been used in the proof of Onsager conjecture for general spaces using whatever. So, and similar thing also in the, I stop here.
Absolutely.
Because similar criterion has been used by Pardos, Whitman, and myself within you, that if you have uniform, but we did it with Hölder, not with these fancy averages.
But in 3D.
In 3D, yes. I mean, like it's the same your assumption. My point is like you need uniformity. That's my point. Then you can conclude that there's no dissipation anomaly for 3D. So that what I'm trying to say is that this kind of like assumption one or something like that is in some sense the natural thing. You do it for 2D because you have other tools, you have other regularity, etc. For 3D, you don't have it, but nonetheless, this has been utilized in other. That's my comment.
Absolutely.
So there's a hidden kind of like structure of Hölder or Bessel, if you want.
But can you explain for people like me why the angular average makes a difference?
What?
Here the which is different.
No. It is basically Hölder is too strong.
Okay,
So Hölder is for pedestrian.
Okay.
You do averaging, you can squeeze more juice.
Okay, just the fact that you're.
Yeah, yes. That's
You
So it's average.
in principle,
Bessel is like if you want some sort of average.
Yes.
you could
So
divide by R to the alpha. And then you see that basically, the derivative is, it's like you have an alpha derivative.
So,
I like it. It's like we Bessel versus Sobolev versus classical. So that's why I want to make this connection.
but in the hand waving,
Exactly.
this language is more or less the same.
Yes.
So we are moving from circular function to under exponent.
So
And what about alpha equal to 0? It'd be an interesting case.
Alpha equal to
No.
Yeah,
zero,
that's okay.
and you don't have anything,
You don't have
Just
anything,
L2.
but
just out.
it's just
you need the power law. You need a model for Gleichen or something. You know, you need turbulence as decay, cascade. Something.
no, of course, yes.
Michel there uses L3 based structure.
Sorry?
Michel there uses L3 based structure. This is L2 based structure. Is that a difference in physics?
If I use an L3 based instead of L2,
You have this dissipation that is L3.
I let her answer, then I can make.
I don't know if I understood your question. If I substitute L2 for
No,
L3,
Duchenne and Robert,
sure,
when they address the Onsager conjunction, not Navier-Stokes,
sure.
they modify the equation and introduce some term, which is like your R or whatever, which is gives you like a defect measure. And then the estimates, they look for structure functions in L3, not in L2. Not S2. Not S2, they took S3, not S2, like cubic instead of that for the purpose that we need. But that's, yeah. But in her case, it is about viscosity. In other words, Duchenne Robert regularized Euler by convolution. In her case, she says, no, I don't regularize Euler by doing mathematical trick. I use Navier-Stokes as a regularization of Euler. And now what can I say? So this is the difference, which is naturally, Navier-Stokes is a nonlinear regularization of Euler. While if you take Euler and you hit it by
It's also
convolution,
the physically
it's just
realistic model,
Exactly.
by the way.
The ideas are some small floating. It's like, how do we do it? Do you use nature or do you use ad hoc? Duchenne Robert used some of ad hoc, but the ad hoc is more like filter. In her case, she let nature in a nonlinear fashion regularize Navier-Stokes by regularizing Euler by Navier-Stokes. And there you need the, as you pointed out, they need the exactly this modulus of continuity for the defect measure. Now she needs it for the S2.
They also have it for that stuff.
Yes, sure, both. Well, thank you very much. So we meet tomorrow.
Yes.
Thanks again.
With that.
Same time. Thank you. Very nice, very good.
I need to send you that.
Exhausting and extensive, exhaustive.
And we should have a dictionary with all the spaces.
Oh, no, there's some more to